Hello everyone, I've just seen a video demonstrating a quantum mechanic experiment whereby we're supposed to see that the quantum object of light collapses into a classical object at the moment of observation or measurement. And I have to say, I'm a little bit perplexed, not because of the quantum mechanics, but because of something else. And I think you'll know what I mean when we watch the video. So basically there's a very good YouTube channel called Looking Glass Universe, where she does many experiments showing quantum mechanics. And I urge anyone who's interested in the subject to go and check it out. She's done her PhD in theoretical physics at the Cambridge University, and the experiments are done very well with a lot of interactive explanations. So let's see one of those experiments.
In the double slit experiment, you shine light on two very narrow slits, which I've represented here like this. And you can see that the light sort of spreads out and it goes through both slits. In fact, we know that this is what happens even with the laser because you can actually see it. If light is somehow wave-like, then this kind of makes sense because it's like saying the wave will spread out and then it will go through both of these slits and make new little waves. Eventually, these two little waves will spread and overlap. And as you can imagine, when two waves get in each other's way, they interfere with each other. And this is what causes the classic double slit pattern. This is a double slit, which hopefully you can see. And now I'm going to put the double slit in front of the laser and turn off the lights. Let's see what happens. And this is what the pattern looks like. And just as a side note, I never get over how beautiful this looks. Just crazy. And so now you get this double slit interference pattern, which looks like a whole bunch of little dots, right? Like there are these sort of bigger regions, and then in each of those regions, there's like little sub-regions as well. That's the double slit pattern.
So I'm going to pause it there for a second and just give the broader context of this experiment. Basically, the double slit experiment was devised to show that light propagates and manifests as a wave. And to explain how the experiment does this and why it does this, we have to take a short detour into the world of shipping design. Now, have you ever wondered why ships have this bulbous thing at the front? Basically, it's designed to create a wave over here. The reason why they put this thing here to create this wave is that there is a second wave that is happening as the result of the bow pushing the water out of the way. So the bow creates a wave like this. Now, where you have two waves peaking and troughing at the same place, they cancel each other out, and you actually get a flat line or flat water. In this case, the water still has a little bit of wave, but it's considerably less than without this bulbous thing at the front. So the first principle of wave dynamics is that if you have one wave interfering with another wave where the trough and the peak coincide, they cancel each other out. Now the length of the ship is also designed so that as these waves reach the back, they trough just at the point where a stern wave would naturally rise up, like this. So these waves, as they reach the back of the ship, they trough in line with that stern wave, and again a cancellation happens. This is all designed so that ships can go down narrow canals without upsetting small boats with a massive wake. So it significantly reduces the wake that is created by the ship. Now if we look at the double slit experiment, this is exactly what is supposed to be happening. We have the light source here, and the light goes through the two slits, and we have two sets of waves, identical wavelengths. But as we scan across, there's the wall where it's being projected. As we scan across this wall, we have a different combination of trough and peak. So you'll get places where two peaks coincide, and that will be an area of intense light. But you also get places like here, where the peak of this wave coincides with the trough of these two waves, and you'll get no light there. So the pattern, the interference pattern on the wall has these little bands of light and darkness as it scans across, and it's as the result of the geometry between these two slits. As you scan left or scan right, the distance changes relative to the two slits, and that puts out of sync the two waves. And this is why the experiment supposedly proved once and for all that light propagates and manifests as a wave.
So when we imagine light as a wave, we're usually thinking of the wave sort of waving up and down, right? Like these are all the peaks of the wave, and they're sort of up and down. But actually, light can be a mixture of all kinds of directions of these waves. Like they could be waving left to right, they could be waving like this or like this. And this light is just going to be a huge jumble of all kinds of different directions. But what if we used this stuff to filter out the light? So let's say that we have some light coming in some random direction here, but we only let through light that is oriented up and down, like this. So only this light would be able to go through. Or what if we turn the filter around and now it only would allow light going this way? So this light would go through, but nothing else. Well, we could do that and it wouldn't really do much for us. But here's the really clever bit. Why don't we do both? Why don't we put a filter in this direction over just the left slit and a filter in this direction just over the right slit? That means that light that makes it through the left slit has to be oriented like this, vertically. And light that makes it through the right slit has to be oriented like this, which is horizontal. What we've just done is we've marked these two slits. The light coming out of them are very different. And so if we want to know whether a bit of light is coming from the left slit or from the right slit, all we have to do is put a filter like this. Because a filter like this will only allow through vertical light, and it won't allow through this horizontal light. And so by measuring this polarization, we've also measured which direction the light went through, and we've collapsed it to only going through one, which is the left slit.
So at this point, one starts to be a little bit perplexed. Why are we describing this as being measuring or collapsing or observing the light when we can see, everyone can agree, we're just blocking the light from one of the slits? If I have two pairs of very expensive polarizing sunglasses, these aren't them. I went to a supermarket and did this experiment without having to actually buy them. If you look through the two pairs and you rotate one of them so that the polarization lines up with the polarization of the second pair, they will actually block the light coming through. So as you rotate from 90 degrees to 0 degrees, at some point you won't get any light coming through at all. With one of the slits, this is exactly what is happening. The slit has a polarizing filter in one orientation, and then she introduces a second filter, and so the light through that one slit has been completely blocked. And so obviously all we have is one slit left, shining light through, and so we get an interference pattern of a single slit on the wall. We can predict all this just with the polarizing lenses. We don't need to interpret it in terms of observing the light or measuring it or collapsing it from a quantum position into a classical position. So why are we then interpreting this experiment in very convoluted and complicated terms when our common sense can tell us what's going on anyway?
So let's see if this really causes measurement collapse. This is the new pattern, and you can see that it actually looks quite different. Like the big patches are still basically where they were, but now there isn't these little lines in them. And just to see how different this actually looks, let's turn the camera around. You can see that there's basically only one beam that's really visible, which is the middle beam. The tiny little beams that you see in the double slit pattern are mostly gone. So observing this light really did change it. Just to double check that we really have collapsed this light into just going through one slit, I compared this pattern to what would happen if you did just have one slit to start off with. And you can see that they look very, very similar. The spacing of these bright bands is pretty much identical, which proves our hypothesis that observing the light really collapses it.
Again, why interpret it like this? We're not observing the light and collapsing it, we're just blocking it, blocking one of the slits with the polarizing filters. But regardless, now she takes away that second filter, so we now have light coming through both slits again. And yet, still, we have a single slit interference pattern. Why is that the case? Well, she explains it with quantum mechanics, but I'm going to demonstrate that we can explain it without quantum mechanics, just with wave dynamics.
So this filter here is what allowed us to know that the light is going through the left slit. But what about if I just remove it? Here's what the light looks like with the filter, and here's what it looks like without. It's basically the same. It just looks a bit brighter without. So what on earth is going on?
Well, what is going on? Well, let's return to our ship again and the waves that are getting cancelled out. So we have the bulbous thing at the front creating one wave, and we have the bow creating the second wave, and the two cancel each other out. If we look at waves, in order to cancel each other out, they have to be oscillating like this. Now, it ought to go without saying that this can only happen if the waves are orientated in the same axis. The ocean waves go up and down. They don't go left and right. But now, with one of the filters in front of one of the slits, we don't have two waves going up and down. We have one wave going up and down and one wave going left and right. The wave going from one slit, left and right, cannot cancel out the waves going up and down. And when we remember that the double slit experiment interference pattern relies on the waves cancelling each other out, then we can instantly see that if the waves coming from this slit are waving left and right rather than up and down, that cancellation cannot occur. And so, lo and behold, we get an interference pattern on the wall of only a single slit interference pattern. The other thing that's important to remember is that the orientation of the slits also must be playing a role. The slits are orientated vertically, and it doesn't take much to realize that a wave passing through a slit which is orientated vertically is going to interact with it differently than a wave going horizontally through that same slit. So it should be no surprise that one of the slits has been nullified in the process of polarizing the light. Okay, well now she's going to add a second filter again, but this time not at 90 degrees to the first filters, but at 45 degrees to the first filters. Let's see what happens.
But our story's not over yet, because I want to show you the craziest variation on this experiment yet. So far we said that having these filters on top of the double slit marks which way the light goes, and since that information has leaked into the environment, it collapses the light to either going through the left slit or the right slit. But if that's true, then how do you explain this? Here we've got the single slit pattern that we've gotten used to, but I can actually recover the double slit pattern by putting a filter in front of this, but not in the direction that we were doing before. If I put it at this 45-degree angle, you can see that I actually recover the double slit pattern. I just think this is insane. How crazy is that? You can see the double slit pattern just pop back out. It's even crazier when you look at it this direction, where this is the single slit pattern, which we expect because of our observation. And here is the filter. And look, It brings back the double slit pattern. The double slit only exists in front of the filter, but behind it, like, you can just see the single slit pattern. Remember, light that's coming through the left slit is vertical, and light that's coming through the right slit is horizontal. But if I put a 45-degree filter in between, what happens is that this light has a 50% chance of going through, and this light also has a 50% chance of going through. So after this 45-degree filter, firstly, both bits of light will now be oriented 45 degrees. So they'll both be oriented kind of like this. And any light that's gotten through this filter is equally likely to have come from the left or from the right now, because both of them will have been polarized in the 45-degree direction. And so, in a way, this filter undoes what this one did.
Okay, now this might seem complicated, but it's actually very simple if we go back to our polarizing sunglasses. Remember, as I rotated the sunglasses, there's a blackout point only at the specific angle of 90 degrees. At every other angle, we can see light through it. So at 45 degrees from each other, the sunglasses let through roughly 50% of the light. Now, I'm going to illustrate this diagrammatically to demonstrate what happens as a result of this 45-degree filter. Imagine we're now looking head-on at the light source as it comes through the two slits. So here's the right-hand slit and here's the left-hand slit. This is without filters, and so the light waves are polarized in all 360 degrees through both slits. But now we introduce our filters. So, and on this side, the polarizing filter is polarizing light through the vertical. In other words, it's letting through light which is polarized only vertically. On the left-hand side, we have the filter which is letting through light which is polarized only horizontally. But there is a gradation of degrees between that horizontal and the vertical where the light fades out to nothing, and the same with this one, where it fades out to nothing. And if we look at 45 degrees of both of these, we see that there is the same intensity light, whether the 45 is that way or the 45 is that way. We get the same amount of light coming through. She says it's 50%. Let's call it 50% for now. So the second filter, let's draw it in like this. The second filter is polarizing the remaining light at 45 degrees from the original filters. Now this means that from the first filters, this high intensity of light has been subdued, and this high intensity of light has been subdued, and the second filter has made primary, as a priority, the light traveling at this polarization and this polarization. So we now get from the second filter light which has been prioritized at 45 degrees, and all the other polarizing and all the other wavelengths have been subdued. Now the second filter, what it has done is it has synchronized the polarization of the light coming through the two slits. We now have light coming through the two slits which is waving in the same orientation. It's no longer waving in opposite directions. And once we get light which is waving in the same orientation, we then expect to see our double slit interference pattern again, because the waves are going together and they have now the chance, when they're offset, to cancel each other out. So she's right, the second filter does undo what the first two filters do. It does restore the double slit interference pattern, but we can explain why it does this just by the interaction of polarizing filters. We don't need to reach into that strange realm of quantum mechanics where somehow observation changes which path the light is taking. Now, no doubt there are experiments out there which require quantum mechanics to explain them. I haven't seen any of them yet. But if we zoom out of this whole discussion a little bit and ask the question, how would Goethe interpret this experiment? After all, he had a very different interpretation of Newton's understanding of optics. And I'm very well aware that in explaining this phenomenon, I'm using wave dynamics. And I'm very well aware that Goethe would hesitate in reducing light to a wave. So I actually find it more interesting than the wave theory of light or quantum mechanics. I find it far more interesting to try and understand the experiment in the way that Goethe would try and understand it. What is the experiment a version of in reality? For starters, we can see that it's very similar to a pinhole camera, which is actually very similar to the human eye. We have light that is passing through a very small hole and is being projected on a wall. Now, this hole isn't a pinhole, it's a slit. And the light isn't just ordinary light, it's a laser. And therefore the pattern on the wall is rather tortured, I must say. It's not exactly a wholesome demonstration of the essence of light. Are we actually grasping what the essence of light is? Do we ever see the light with our senses, actually? When you look at a painting and you say, wow, look how the artist has painted the light. The artist hasn't painted the light. In fact, the artist has painted the shadows. The light has been conjured up by your own inner eye, seeing the light in the picture. The light, real light, we don't see with our eyes. We see it with our inner eye. It's a supersensible reality. What is happening to this light, this supersensible light, in this experiment? That's a far more interesting question. But I think I'll leave it there. Maybe we can address that in another video. I hope this has been interesting, and thanks for watching. Bye.